Welcome to this explainer. Today, we're stepping into the dojo of rotational dynamics to master the spin.
Head spinning? Don't sweat it. We're going to uncover the hidden rules behind how all these objects move.
First up, direction. Curl your fingers with the spin and boom, your right thumb shows the angular velocity.
Here's the wild part. Moving at a constant speed in a circle actually requires constant acceleration.
Now, let's pit the real inward centripetal force against the totally imaginary outward centrifugal pseudoforce. On a merry-go-round, you literally feel pulled outward. But guess what? That's just the centrifugal illusion. Check this out. Static friction fights gravity, while the wall itself pushes inward, providing that centripetal force. So what happens when a spinning object gets heavier? Let's unlock the secret of the moment of inertia. Just like regular mass resists linear movement, moment of inertia is an object's fundamental resistance to spinning. But it's not just about the total mass. It's exactly how that mass is distributed around the axis. This means different shapes with the exact same mass will actually resist spinning in completely different ways. Basically, everything you already know about linear physics translates perfectly to rotational physics using this simple cipher. Now, let's tie this together with our ultimate technique, the conservation of angular momentum. This law means that if you change your inertia, your spin speed absolutely must change to compensate. Think of a spinning ice skater. Arms out means a slow spin. Pulling them in unleashes incredible speed. Or a diver, tucking their body slashes their moment of inertia, letting them multiply their flips. We've mastered spinning in place. But what happens when these objects start actually rolling forward through the world?